Number 56. Find the direction and magnitude of the force that each wire experiences in figure 22.58 letter A by using vector addition. All right, so strap on your seatbelts. Let's go for a ride. All right, we got to look at this picture. Again, we got to find the basically magnitude and direction of the forces on all three of these wires. Now, this problem is going to kind of mimic problems that we've covered in the past on electric charges and their forces, right, on a whole series of charges in the problem, right? You might remember a problem similar to this, like almost if you had a charge here and a charge here and a charge here, and we had to calculate, let's say, the net force acting on that charge produced by these two. It's the same idea, okay, as that type of a problem. Obviously, the formulas are different, though. So what I'm going to do is let's just start off by kind of drawing a little picture. So here's the picture, okay? And in the picture, they tell us that these currents here are separated by distances of 0.1 meter. They said 10 centimeters, but you know we need that in meters, so that's simply going to be 0.1 meters. Now, it's an equilateral triangle, that means, and therefore all the angles in here are going to be 60 degrees. That might be handy later on. So let's first calculate the force acting on this current, and that the force acting on that current is produced by the magnetic fields of these two currents, okay? Check out number 55 for an explanation. So we know here that the current here is coming out of the page, right, towards you because it's a dot, and then the currents here are going into the page because that's an X. Now, first thing I want to do is I need to look at each of these two currents independently of one another. So what I'm going to do, maybe let me make this one red, okay, and I'm going to make this one blue. So now what I have to do is, in order for me to find the net force acting on this current, I have to identify the magnetic field being produced by this current and how it affects this current. And then I have to identify the magnetic field produced by this current and how it affects that current. Okay? So I'm going to look at it independently. So now consider using right-hand rule number 2. If I know the current here is pointing into the page, that means your thumb has to be pointing into the screen. All right? And if you then curl your fingers around the current, you would be curling them in a clockwise direction, right? Around that current. If your thumb is pointing to the screen, right? Right-hand rule number 2 says, as you curl those fingers, that's the direction of the magnetic field. So notice the magnetic field is basically, circular around this, right? So it's circular. So when we finally get up to now, let's say this level of circle, okay, what we notice now is that the direction of this magnetic field is still, rotating in a clockwise fashion. So I'm interested, though, only at the magnetic field acting on this current at that exact point. And what I'm going to do is I'm going to draw a line tangent to that point, right? Because at this exact point right here, the magnetic field is pointing in this direction, right? Doesn't that make sense? Maybe let me angle that maybe a little better. Maybe some angle like that, okay? So what I just drew here will now represent the magnetic field, all right? That is being produced on this current by the red current, okay? Because remember, currents themselves produce their own magnetic fields, all right? In order to find the force on this, I have to find the external magnetic field that is acting on this particular current, and one of the external magnetic fields is produced by this current. Okay, hopefully that doesn't sound too circular. A whole bunch of circles. All right, that's as funny as it's going to get. So get the laughs out now, because the tears are coming. So what we realize now is I notice that this creates, and it should create, by the way, a 90-degree angle here. If you drew it appropriately and you kind of saw how that tangent line, it did not line up with this. But the tangent line should create a 90-degree angle. But that should kind of make sense, because isn't this kind of the radius, right, of the circle? And this was a circle around it. So that's always the case. There's always a 90-degree angle at every single tangent point, right, relative to the radius, the 90 degrees there. Okay? So hopefully that kind of makes sense. So just keep that in mind, that that's 90 degrees. All right? I'm probably not going to draw that in yet. Now, what we would do is we would do the same analysis for the blue one. Now, the blue one, using right-hand rule number 2, let's predict its direction of the magnetic field it's producing. So if the blue current is going into the page, point your thumb into the page. Now curl your fingers around, and look, it's going clockwise again. So we get this clockwise thing going on, right? So again, it's going to be this circle out here that doesn't even approximate that very well. That's a little better. Okay, let's move it down a little bit. So now what we're going to find is we're going to find then... Now this is really bad. That's probably a terrible, yeah, that's a pretty bad circle there. But you know, that's good enough. So what we'll realize now is that this particular tangent line is probably going to be coming out in this maybe direction here. Okay, maybe something like that. Okay, and that's now the magnetic field at this particular point acting on that particular current produced by the blue current. All right, so let's just leave that as B. All right, so let's delete this. So now what we're going to realize is, let's draw a little coordinate system, okay, up here, like this. Okay, now each of these are the magnetic fields being produced or acting on this particular current. All right. Now, maybe what might be helpful is if I find this angle here and maybe this angle as well. Okay. So what do you think this angle is? Well, there's a couple of ways we can do it. Let me see if I can move. Well, this is pretty sloppily done. So let's move that on over a little bit. Now keep in mind, focus, that over here is a 90-degree angle. Okay. And also remember that the angle inside of here, I'll try to draw that in red, the angle here is 60. So what that means is that if this total angle was 90 and this angle here was 60, what's this little piece then? Well, that little piece would be 30, right? That little piece would be 30. So you can write in your little 30 degrees here if you want. Okay, but how does that help us? Well, keep this in mind. Remember this angle was 60, right? Now, if I cut that angle in half, how much is this piece? Well, you say 30. And I say yes. And then I might ask, well, how much is 30 plus 30? And you would tell me 60. So what I'm telling you now is that this angle right here is 60 degrees. And what does that mean? Well, that means that this angle in here is going to be 30 degrees now, right? So I'm just going to write now, you don't have to use this particular angle, but I like to reference it in terms of the x-axis, not necessarily the y. But you could do it. It doesn't matter. We're all going to end up at the same place. So that's 30 degrees. All right. Now, for the same reasons, try to figure this one out. All right. But you probably already noticed it's probably also going to be 30 degrees. Okay. So that should hopefully, you know, think about how to find that one now. You can also take, you know, these into account. You know that this right here must have formed a right angle. Okay, remember, because this is like the radius of that circle. So this would have formed a right angle in there. Okay, and you knew, and then what if this is 90 degrees in there, and this was 30, and that was 30, that's a total of 60, and then there's a remainder of 30 left over. So that's why that's 30. Okay, so now, those are just, by the way, the magnetic fields. All right. We can take this problem in a couple of different ways now, but I think what we're going to do is I want to find now the forces produced by each of these currents independently of one another. So what I'm trying to say is this. If you have this current, okay, that's pointing out of the page. Now I'm using right-hand rule number 1 because I want to predict the force, okay? I want to predict the force based on the direction here of this magnetic field. So if the current here is pointing out of the page, take your thumb, point it towards yourself. Then you have to now align your fingers. Remember right-hand rule number 1. If you need a refresher, take a look at number 1 of this chapter. Okay. Point your fingers now down at an angle about 30 degrees below the horizontal. Now, if you have your hand in that position, I would draw it, but you know my drawing skills. They're absolutely abysmal. So what we know now, though, if the hand is in that position, then the force acting on this must be at a 90-degree angle relative to that magnetic field vector. So it's going to be pointing here somewhere, okay? Right about here. Right, your palm should be facing off in that direction if you're orienting your hand properly. So now what I realize is that this is the force vector. Okay? That's the force vector. That is acting on the black current there, which is produced by the red current, the magnetic field of the red. Okay? So now, what is this angle in here then? Well, you can think about it, right? If this total big angle over there is 90, and this is 30, that's 30, well, that leaves 30 left over, right? So this is 30, and that's 30. That means that going all the way back to the horizontal should be 60. All right? So that's what I'm going to now note. All right? I'm going to draw in that angle of 60. Okay? 60 degrees. Now, what I'm going to do here to simplify the picture a little bit, let's erase the blue. Excuse me, that's red. Let's erase the red one. Okay? Because we don't need the magnetic field anymore. We know the direction now of the force. All right? Now, I got to do the same analysis for the blue one. So take your thumb, point it out of the page, boom. Then angle your fingers now up at a 30-degree angle, okay? And what you'll realize is now your palm should be pointing off in now this direction, okay? That now represents the vector of the force acting, okay, on that current. All right, and like I said, if this is troublesome, what I would do is I would probably start reviewing some of the right-hand rule stuff, the basic ones, okay? Now what I'm going to do here is I'm going to get rid of, well, actually, then what is this angle here? Or this angle, you know, you can calculate a whole bunch of them. It depends on what you want to do. So remember, if this is 90 degrees in here, all right, and if that's, I mean, there's a whole bunch of ways to do it, but if that's 90 degrees, and you know this little sliver in here was 30, because of what we talked about before, then this total piece needs to be 60, right? And if this total piece is 60, but yet this thing cuts it in half, then this little piece here should be 30. And if that's 30, then to the x-axis, that should be 60. And it should hopefully then make sense based on the picture, right? Based on how these are kind of oriented. I tried to do my best, proportionally. All right? All you can ever ask for is your best. So let's get rid of this, erase it, and now that's what we're left with. Here's the picture, okay? What we now have to do is we now have to find the net force. Okay, we now have to find the net force. So how do we do it? Well, I notice I have two force vectors here acting on that particular point, and now what I'm going to do is I'm going to look at them independently. So let's calculate the one in red, okay? So the force acting on this black current, okay? The force acting on the black current. Oh, and by the way, the formula here I'm going to use was created in basically number 55. So please take a look at number 55. I'm just going to use it right here like this. All right? So this is now the force acting on A, produced by some other, current is going to be equal to 2 times 10 to the minus 7th multiplied by the current of A times the length of A times the current in B divided by the distance between them. Okay? Now, we realize, well, wait a minute, Andrew. You said the length of the length of the wire here for A. They didn't tell me any lengths of this particular wire. How the heck are we going to do it? Great question. We're not. We don't know it. So the question is, find the direction of the magnitude of force. They really should be saying, find the direction of the magnitude of the force per meter. All right? There's no way to actually find the absolute amount of force. The only thing we can do is find the force per meter. So that's what we're actually solving for, just so you know. So here now, what I realize that I can find this now for the red one. Okay, so let's put everything in red. So let's color this. Okay, and there's the red. All right. Now, what's A and what's B? Well, A is the wire you're finding the force on, and then the B is the current that is producing the magnetic field on that wire. Okay, that's the whole idea. So let's start plugging in some values. So this is A, L of A, and this will be 2 times 10 to the minus 7th. That's now the current of A, which they told us, by the way, was 5 amps. Are you having fun yet, by the way? If you're still with me, good job. And if you're not, I totally understand. But you'll never know that I totally understand because you're not listening. So here, the distance between them is what now? The distance between the two currents is going to be, or the two wires, however you want to think of it, because the current's traveling in the wire, right, is going to be 0.1. So simply now calculate that. Take out the calculator. 2 times 10 to the minus 7th multiplied by 5 times 10, all divided by then 0.1. So this is 1 times 10 to the minus 4. So that is the newtons per meter, amount of force acting at this direction, okay, relative to this charge. All right. So let's get rid of this little a here. We don't need it. And let's write that down. I'll put it on the upper right, left-hand side. All right. Okay, now let's do everything for blue. But if you notice, there's only going to be one little change. So let's change this color. Let's do blue. Okay. The only thing that's changing now is the current here. So what I should have written down as well, which I didn't in the picture, but I'm trying to keep it less busy, they gave us the current is 20 amps, okay, for this particular current. So instead of 10 being here anymore, it's now going to be what, ladies and gentlemen? 20. So it'll just be 2 times that value that we found before. So this simply now will become 2 times 10 to the minus 4th. And let me just actually redo that calculation just to make sure I didn't make a mistake. All right, so 2 times 10 to the minus 7th, 2 times 10 to the minus 7th times 5 times 20 divided by 0.1, and good. Okay, so everything looking good so far. So here, so we got that magnitude, okay? That's the force per length of the force per meter. Now, this goes back to like chapter 4, right? Easy stuff now. Find the net force. You have your directions here. All you got to do now is find the force, all right? So, so how do we do that? Well, we're going to do it simply like this. Use your component table, X and Y, right? We all love our little component table. And let's do it. Now, this one I'm going to kind of run through because, you know, components are, this is easy peasy at this point. But if you need a review of, you know, the components and stuff, please check out like, you know, the chapter 3, chapter 4 stuff. All right. So here, the X direction, it's negative. So I'm going to plug in a little X. This is for my blue one, a negative there under the X category. And I'm going to take cosine of 60, multiply it by then the blue hypotenuse essentially of that triangle, right? So that's times then 2 times 10 to the minus 4th. So that's negative 1 times 10 to the minus 4th. Okay, great. Now, how about the Y component? Simply do the sine. So sine of 60 times then 2 times 10 to the minus 4th. And here we're going to get a value positive, that is 1.73 times 10 to the minus 4th. Okay, now on to the red one. So same thing, all right, here's the X. It's positive this time, so leave it alone, or you can write a positive sign, that's fine. And we're going to do 60, right? So cosine of 60, because I'm finding the X component, multiplied then by the magnitude of that red one, which is 1 times 10 to the minus 4th this time. So times 1 times 10 to the minus 4th. And here's about 5 times 10 to the minus 5th, all right? And then the sine, to find the Y, it's positive also. So 1 times 10 to the minus 4th times the sine of 60, and 8.66 times 10 to the minus 5th now. All right, so how do you find now the resultant components? Well, you simply got to add them all together, right? So the resultant force here, you're just going to literally add them together. Obviously, if one's negative and one's positive, it's really a subtraction, but you get the idea here, right? So negative 1 times 10 to the minus 4th plus then 5 times 10 to the minus 5th. And we get negative 5. Oops. 1 second. Negative. Where's my thing? Negative 5 times 10 to the minus 5th. And then how about the Y's? Add them together. So I'm going to use the exact values. So take those two values there and add them. So I get about 2.60 or so. 2.60 times 10 to the minus 4th. Now, those are the components. Right, now we can find the actual resultant vector, all right, by doing our little almost inverse of the Pythagorean theorem, right? The square root of then the sum of all the x's squared. We've seen this now way back when, sum of all the y's. And we're going to plug it in. So this is now negative 5 times 10 to the minus 5th, square that, okay, plus then 2.6 times 10 to the minus 4th, square that. Add them together, take the square root of it, plug it on in, and let's see. So square root of then 5 times 10 to the minus 5th squared. I know it's negative, but you know when it's squared it's positive. So plus then the 2.6, I'm going to use that exact value and square it. And what do we get? So here we get a value now of about 2.65 or so, considering the rounding, times 10 to the minus fourth, and that's still going to be in newtons per meter. Remember, here I'm not going to keep writing over L because, you know, it's just too much work. This problem is already ridiculous. So anyway, that's the force, net force. Now what's the direction? So you remember your formula, theta will equal the negative tan, not negative tan, what am I talking about? Inverse tan of then the y value over the x, right? The y coordinate over the x. So here it is, right? Simply plug it on in. So there's going to be 2.6 times 10 to the minus fourth. I'm going to plug in that exact value. Or you can plug in the -5 or do it positive. It really doesn't make a difference. All right. And then what are we going to get here for the theta? I'm probably going to plug in the positive because then I just know it's relative to the negative x-axis. I know, right? You already know, based on these components, what quadrant the resultant vector should be. A negative x and a positive y only shows up in this quadrant number 2. So, you know where it is. Inverse tan then of that exact value, 2.6 from before. Just give me 1 second. There it is. Divided then by, make sure you calculate it in degree mode, 5 times 10 to the minus fifth. And here we get a value of about 79.1. And that means 79.1, right? Because the resultant vector would be roughly about here. What I just found is I found the 79.1 degree angle. That's relative to the negative x-axis, okay? So 79.1 degrees. So how would you answer now this question for just the first part of this 3-part process? You would answer it as 2.65 times 10 to the minus 4 newtons per meter at 79.1 degrees above the negative x-axis if you wanted, or you could state it in terms of the positive x. You can say counterclockwise, clockwise. You know what? There's so many ways to phrase this. All right. So don't get too caught up in that. Just make sure you understand what we're talking about. Okay. At then 79.1 degrees above the negative x-axis. That's good enough. All right. And that's then the answer for 1 part out of this 3-part problem. Joy. So where am I going to put this? Okay, so now let's erase all this. And let's put that on the top. Isn't this fun? All right. There's one answer. I probably shouldn't. Should I have erased it? I don't even know. Whatever, that's one of the answers. Actually, I think I'm just going to erase that too, because I'm going to need all the space I can get. So redraw the picture. Let's see if I'm going to go a little faster now through this. And by faster, I mean instead of, what is it, 17 minutes already? Oh, it's only 23 minutes and I've only done 1/3 of the problem. Oh, that's okay. Right? I'm sure you're still with me. Here I am talking to myself. Point 1. Again, what I'm going to do this time is let's do this one in blue. Oh my goodness. I'm going to go nuts with this problem. Okay. And here now we're trying to find the, forces on that. So let's first talk about the magnetic field. If this thing is pointing, now I'm going to run through this. Okay. If this thing is, it's probably still going to be like an hour and a half long. But if this current is pointing out at you, your thumb is pointing out, the rotation then of this magnetic field is going in a counter now clockwise direction. So that means when I make the big circle around that X, see if I can do that. Okay, it should be now off in this direction. All right, off in that direction. Now I think what I'm going to do is I'm going to let me erase this right now. Let's put that back in blue. I think what I'm going to do is I'm going to turn this, because it doesn't matter if it's coming in or out of the page actually in this problem. So the forces, because the magnetic fields are all 90 degrees. So what I'm going to do here is, well, actually, no, it does. I lied. I just lied to you. So let me leave it as an X. I was going to try to just represent it as a dot, but I can't. So let's dot a line. Just like that. Okay. Now quickly, this creates a 90-degree angle for reasons we discussed before. you know that then this is 60 in here. So if this whole thing is 90 and that little part is 60, then this has to be then 30. Okay, 30. And that's B. Then for this one. Now this one is coming out of the page. No, into the page, excuse me. Point your thumb into the page now, curl your fingers around, and you realize it's going clockwise, right? So when we draw our big circle now, with hopefully that in the center somehow, that's not even going to look close. And I guess maybe something like this. Sure. That's close enough. So now when we draw that, right, we realize that oh, look at this, right? Oh, that's nice. What happens here? This one is pointing directly now up, right? Look at that. So this one's going directly up, right? Because remember, it's clockwise, right? So it's rotating around the magnetic field. Thumb into the page is right-hand rule number 2. Rotating around clockwise, so at that exact point is pointing up, okay? So let's now get rid of that circle, and let's just point that baby straight up. Okay, and let's write B. Now I'm going to take a look at the forces of each. So if the current here is coming out of the, into the page, point your thumb into the page, angle your fingers now 30 degrees below that horizontal, okay? And then your palm should be now directed this way at a 90-degree angle relative to that. So this is technically the force, right? And now we can go about finding this thing on out, right? If this is 90 degrees in here, and this is going to be 60 degrees, right? Because that's 30, and this created another 90-degree angle right in there. What am I even talking about? So this had to be 60, and yeah. And then the remainder here is going to be 30. And then that means the remainder here is going to be 60. And that's really the angle I want. I want it in reference to the x-axis. So that's the force, okay? So now, erase this. Now do the red one, okay? So current is going into the page, point your thumb into the page, right? Just point your fingers now straight up. This is right-hand rule number 1. If your thumb is into the page and your fingers are up, then the force here is pointing directly now to the right. And wait a minute, that makes sense. If these currents, right, are pointing in the same direction as one another, it should be an attractive force, and you notice now this one's traveling towards that, so I think we're on the right track, okay? Now what we can do is just get rid of this red one, okay, because I'm interested in the forces. So now what I'm going to do is I'm going to use that formula we had before. Boom. Let's do this one now for blue. So color it. We're going to do it for blue. Yep, got to do that little trick from time to time since the program kind of stinks. There's a lot of glitches. Anyway, so we have to, right, divide this on out because we're finding the force per area. Bring that on in. And let's start plugging in the numbers. So here F, I'm just going to do F over L here for the blue. 2 times 10 to the minus 7th. The current in A. So what is A? Well, A was the current of interest. So what's that current? Well, it was 10 amps. Okay, so plug in your 10. The B one now, it was the current up here, so that was 5. Divide them by the distance between them, right? So that's 0.1. Oh, wait a minute. You might be saying, huh, that's the same calculation as before. Yes, it is. Yes, it is. So now what we're going to do is we're going to solve that, right? So plug that on into the calculator. So 2 times 10 to the minus 7th multiplied by 10 times 5 divided by 0.1. And this is 1 times 10 to the minus 4. I'm just going to call this F. Just remember it's newtons per meter. I might even forget that, but, you know, please forgive me. So this is 1 times 10 to the minus 4th. Newtons per meter. Okay? And that's for the blue one. Okay, great. Now we're going to do this for the red. The only thing we got to change is the value of one of them, right? So color. Oh, yep, colors aren't there. Oh, look, now they're there. The 10 isn't changing, but now it's going to be this one that's changing, so that's now 20, right? So instead of the 5 over here, you're going to put in the 20. Distance still stays the same, so that's great. So let's plug that on in. So that's 20 times 10 to the minus 7th, multiplied by 10, times 20, divided by 0.1. 4 times 10 to the minus 4th. Okay, great. So now that's newtons per meter. All right. And I think, if I remember correctly, that the other one was 2 times 10 to the minus 4th. So when I do the third one, I'm just going to memorize that value. All right. Now, you're probably like, what is this guy talking about? I don't even know at this point. Now what we got to do is we know, I said I was going to run through it. What is that, 7 minutes already? Okay. So now we know the blue force value. We know the red force value. We got to find the resultant component table. All right. blue one. So here's 60. We know the magnitude of it. So what you're going to do is the x is negative, so be careful. Plug in your negative sign, and now do the cosine of 60. Cosine of 60 multiplied by 1 times 10 to the minus 4th. So this is 5 times 10 to the minus 5th. What's the y value there? Well, now you're going to do sine. So sine then of 60 times 1 times 10 to the minus 4th. And there we go. 8.66 times 10 to the minus 5th. Okay, sounds good. And by the way, that is also negative. Careful. Oh boy, that would imagine that. Be careful. Okay, and now we're going to do, thank God, this one's exactly on the axis. And now we're going to do, the x value here is just simply 4 times 10 to the minus 4th, and this is 0. Oh my goodness, thank you. Okay, this was the blue. This was the red. Let's find the resultant. Isn't this fun? I told you to strap in, right? So let's add those two together. So it's a negative 5 times 10 to the minus 5th plus 4 times 10 to the minus 4th. 3.5 times 10 to the minus 4th. So it's in the positive x direction. And now y, though, is going to maintain its negativity. So it's 8.66 times 10 to the minus 5th. So x is positive, y is negative. What quadrant are we even talking about? Well, we got to be talking about quadrant number 4 over here. Okay? And the x is larger than the y, so we're probably going to expect it to be maybe somewhere here. All right, we'll see. So let's plug it in. So to find the resultant force now, you know the formula. Square root of this thing squared, so 3.5 times 10 to the minus 4th. Square that. Add that then to negative, negative 8.66 times 10 to the minus 5th squared. Make sure you plug in the square inside those parentheses. So square root of now 3.5 times 10 to the 4th squared. Okay, plus then the 8 point blah, 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 blah squared. And we get a value about 3.6. So the resultant force here, okay, so the resultant force on this particular wire here, okay, is going to be 3.61, I guess, times 10 to the minus 4th. All right, and that's going to be in newtons per meter. Then find the angle. All right, I won't box it in yet. So the angle here is going to be tan minus 1 of the y over the x. 8.66 times 10 to the minus 5th. I'm going to plug in the positive, 3.5 times 10 to the minus 4th. You know I'm just plugging in those values, blah, 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 blah. Inverse tangent now of 8.66 times 10 to the minus 5th, divided then by 3.5 times 10 to the minus 4th. And look at that, 13.89 or 13.9, and that is rough in reference to the positive x-axis. It's just going to lie below it, okay? So that is this right here, my friends, is the resultant, my friends who are still with me, is the resultant vector, okay? And the angle there is 13.9. So here's the answer now, at 13.9 degrees below the x, positive x, that is, axis. All right, and there's the answer. There you go. All right, now there's one more. Let's do it. I'm just going to go through the directions. I'm not necessarily going to go through some of the calculations now because it's just the same thing over and over again for the most part. So now let's just erase our little picture. All right, so you got your two answers. Here's the dot, here's the x, here's the x, here's your little triangle. Now we're going to be talking about this one. So it doesn't matter, put this one in blue, all right, and put this one in red. All right, so now if this current, remember, if this current is pointing out of the page, then it has to be rotated in a counterclockwise direction, okay? And if it's rotating in counterclockwise direction, when it eventually reaches that black, it's terrible. When it eventually reaches the black charge there, that's roughly okay-ish. That's going to be close enough. It's going to be pointing out in this direction because it's rotating in a counterclockwise direction, right? So that's B, okay? Here's the radius, right? 90-degree angle. Okay, so that takes care of that one. Delete. No? Okay. No, I don't want to take a screenshot. No, I just want to delete it, actually. All right. So maybe we should start doing a little, writing a little, our dashes here for this charge. And we got our little now. Dun, 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 dun. Okay. So now maybe I'll just talk about this angle in here maybe a little bit quickly. So if you know, right, this angle in here has to be 30. Why? Because, well, that's 60, so that's 30. If this whole thing was then 90 degrees, what is the remainder? Well, the remainder is going to be 60. And if that's 60, what the heck is this? That's 30. Okay. Now, this current is pointing now into the page, so put your thumb into the page, right? And if you put your thumb into the page, this current is going in a clockwise fashion, okay? So when it eventually reaches that other current, it's going to be pointing, oh, look at that, directly downwards, right? Very nice. Okay. Delete. And this will be the magnitude, and we don't really have to figure out the angle, right? Because that's pretty straightforward. So now we got to figure out the direction of the forces. Okay, so this current here, if you can't see, that's because I can't either. It was an X, right? It's going into the page. So if the current, right-hand rule number 1 now, current's going into the page, angle now your fingers up at a 30-degree angle, and you'll realize now your palm is pointing down this direction at 90 degrees relative to B. So this is the force. Okay, so what is this little piece in here? Well, if this whole thing's 90 and that's 30, obviously it's 60. Okay, so this is 60. 60. Now get rid of this thing. Okay, same thing with the other one now. Okay, so here the current is pointing into the page. Point your thumb to the computer screen now. Point your fingers downwards. If your fingers are pointing into the screen, excuse me, your thumb's pointing into the screen, your fingers are down. The force is now this way. Oh, and look, that's the attractive force we were talking about before. So that does make sense. I think we're on the right track, so just erase this. So here now are the two force vectors. So now you got to find the forces of each, right? So it's actually going to be the same numbers as before, okay? The reason being is because nothing has really changed, right? If you look at the formula here, you know, I find the per area, again, divide that on over, right? The A now is the 20, so this is 20. The B then, in this case for the blue one I'm doing, is going to be 5. So just do that in the calculator. And then the distance between them is 0.1. That stayed the same. So 2 times 10 to the minus 7th times 20 times 5. All then divided now by, oh, no. That one will be the same as, not the blue one there, but the one is before. It's 20. It's 2 times 10 to the minus 4th. Divided by 0.1. Yeah, 2 times 10 to the minus 4th. Right. So that's the one. So this force value was the same as the one we found over here, acting on the blue one. Okay. So basically, this was 0.1, and if you plug that all in, we're going to get the blue value now of 2 times 10 to the minus 4th. Okay, great. The red one here should be identical. All right, the red one should be identical. Just, if you want to show it to yourself, whatever color, who cares? IA is 20, right? That's this one. This is 10, so 20 and 10. Divided by then 0.2, so 2 times 10 to the minus 7th times 20 times 10 all over 0.1. And there it is, 4 times 10 to the minus 4th. So those are the two values we're working with. Now guess what we're going to do? We're going to find those components. So component table X and Y. Okay, great. Oh my God. I'm going to go nuts on this one. Okay, so anyway, blue one. So blue, here's the X component. It's positive, so leave it alone. So it's going to be then cosine of 60 times then the 2 times 10 to the minus 4th. So that's 1 times 10 to the minus 4th there. The y component is now negative, and it's going to be sine of 60 times then 2 times 10 to the minus 4th. Plug in the negative, it's going to be negative 1.73 times 10 to the minus 4th. The red one now, oh, thank goodness, it's just a negative 4 times 10 to the minus 4th, and that's 0. Add them together. Okay, add them together. So you got 1 times 10 to the minus 4th minus basically 4 times 10 to the minus 4th. So negative 3 times 10 to the minus 4th. That's just going to be negative 1.73 times 10 to the minus 4th. This is the resultant force. Where should this be? Negative x and negative y. That's only going to happen in quadrant number 3. And it looks like it should make sense. Okay, now find the resultant by doing... This time I'm just going to tell you how to calculate it. Square root of this squared plus that squared. Okay, square roots over the whole thing. So square root then of 3 times 10 to the minus 4th squared plus then, I know they're negative, but when you square it, it'll cancel out anyway. So you don't even need to plug in the negative sign. But plus then I'm going to take that exact value, square it. So I get 3.46 now times 10 to the minus fourth. That's newtons per meter. And then find the angle, inverse tan with an extra n, minus 1. Nobody's even listening anymore, so it doesn't even matter. It'll be the y over the x, okay? And if you are listening, my goodness, God, whomever bless you, it doesn't matter. All right. So always got to be careful. Always got to be careful. So y over x, so it's going to be, but nobody's listening anyway, so who cares? So it's the y value there, the 1 point, so inverse tan of that divided then by 3 times 10 to the minus fourth. Like it, yeah, 30 degrees. Wow, look at that, 30 degrees. So all that blah, blah, blah is going to equal 30 degrees. And this is at 30 degrees now, okay? 30 degrees, it's going to be relative to what? So it's below the negative x-axis. So you can write below, I'm changing the letters, but nobody's watching, so it doesn't matter. Below the negative x-axis, okay? And by the way, guys, woo, right there, just hit that thing. Just hit it for me on this one, please. Please. If you're still with me, just please do it. Hit the like button too, all right? And hopefully I'll see you in the next problem if I don't pass out, all right? Oh, not bad, only 40 minutes. Okay. Guys, thanks again. Yeah, and I'll see you in the next problem. Take care.